welcome Dr. Prashanta Ghosh to the floor. He's a professor and the program director for electrical engineering at L.C. Smith College of Engineering and Computer Science. So at L.C. Smith, first year use. And Professor Ghosh's current research includes a lot of work in smart grid technology, design, and analysis of micro and nano devices, as well as thin film gas sensors. He is the co-principal investigator for a Department of Energy project titled Multi-Institutional Curriculum Development and Delivery to Create a New Smart Grid Workforce. So he's also a senior member of IEEE, and we'd like to see his work today. I think this is particularly interesting. I've seen before some of this talks about how with all the technologies that we're enabling, there's also a workforce demand side and how to get that skilled up talent that we might need. So anyway, Dr. Ghosh, thank you very much for your remarks today.
Thank you. Again, my name is Prashant Ghosh. Before I start, I want to share that I'm so proud to see Nick here. He was one of my students. I mean, as a professor, that's what he said. So, what I thought I would do is okay, as that program, what Seth meant, is a multi-institutional and what involves Syracuse University, the lead university, Clarkson is there, University of Rochester, Buffalo State, and the University of Buffalo, and our OCC. These are the all institutions involved there. Our plan is to develop, as you said, the workforce smart grid area. For that, we are working on developing programs, certificates in that area, which is associate degree all the way to PhD degree, and that's what we are working. In addition to developing the course, we are also developing the lab, which will have three parts. And briefly, one is basically the lab size of transmission system, lab size of the distribution system, and the third one is what we call smart home lab, which we'll be planning to be here. And many of the things which you mentioned will be there so that we can test different scenarios. So giving that background, with that we are also working in different research areas in the smart grid. So I thought I'll mention two of them, and which eventually I believe will have impact on not only on the consumer side, but also the policy side. So quickly, so for example, we are talking about the microgrid. And that's the basic structure. We have the regular power supply, we have renewable energy, and then we have the basic load, which is our home, light and regular. We have the Syracuse, obviously, not this winter, but usually we need heating. And then these are the new things, CHP, combined heat power and energy storage system. We need that. That's the basic structure of our theoretical study. So based on that, what we said, okay, so what I need, if I just focus on CHP, we can have PV, solar cell, we can have turbine, wind turbine, and all of this. So, for example, we have the grid power, that's all we do is we have the solar cell, we have the CHP, and we do need the energy storage. I mean, what I understand, we do need that, because you can't have a constant supply of solar cell, because sun moves, you can't have wind to speed together. So, but for our home, simply, I need 110 volts and a certain amount of current so that my refrigerator runs, my microwave runs, and all of this. So this plays a critical role. And so, but I'm not going to go into details of that. So now look at this. This is one area. This is the real from New York ISO. This is a winter in the 24 hours. This is a summer. That's the load for a particular area. Now, in this load, this is the electricity load, and this is the heating load. There, the air condition, and so this is real data. So what we did a little before is we said, okay, if that happened, now I'm going to include, let's say, CHP. And I said, if I just include the CHP, is it going to help me at all? Answer is, it probably will help you a little bit, but not the level you want. Because the emphasis of the objective of this work to show that you really have to use the CHP and the other renewable in a certain way, in synchronism of your power supply, then and only then you can get the best result as far as your savings of the money. So for example, this is, as I can say, if I take the CHP and I'm running it 24 hours, all right? But how I control the load, and that's what is being, I'm not going to go details, the different scenarios means. And CHP is there, but look at the price-wise, that how much, that column give you what is the percentage of savings. That's where the skill comes in terms of optimization. So one of the work we are doing is optimizing the different way. And now think about if you have a CHP, if you have a solar cell, if you have a turbine, if you have other things, we got to synchronize it. And this gives you about the percentage cost reduction. And that's actual dollar saving. Here, look at the chart that if we do it like the morning, we all know we don't have enough sun, so we have all the green. In the middle of the day, we can use quite a bit of solar cell. And so this is actually what you are paying to the utility. And so on. So one can try different possibilities. And this is just an example, one of the examples showing how we can save some money. And I'm going to show you, and in a minute I will oppose my count. Yeah. But this is without, this is just said, okay, I got it, and I'm going to include it, and I'm going to save one, and everything is good. But one of the things we many times don't include, that what is the cost of that solar cell? Not only to install it, but to maintain it. And that, when you put that thing in the equation, things change dramatically. So I'll do in another case studies. But in this optimization, what we showed is, look at this. This is without that CHP. And this is the variation in this time span. And if we do the optimization, this is what we get savings-wise. And that, I think, this optimization process can be installed, and more, you don't have to do it. It can do it in an automatic fashion. But that is the savings-wise. Yes.
What costs are used for natural gas?
Yeah, I was getting, we have not included the natural gas.
Oh.
The cost of the natural gas to run the CHP. Okay, and I will show you another case. That's why I made the comment that things change. Here we are saying, okay, I got a renewable energy, one of these, and if I do that,
so just a replacement of, okay.
A replacement of that without including the installation cost and the maintenance cost. But it is a positive principle, and then we'll include some. But at least it says that there is a opportunity to save the money. Yes?
Remind me what CHP is again.
Combined heating power. So you use the natural gas, or latest there you can say that you can drive into the PV solar cell. There is a case on that.
Doctor, just one quick little anecdote. One of the best examples was called FreeWalk. And Honda took a little single-cylinder motorcycle engine, They sell hundreds of thousands in Japan, and it runs on natural gas. It's a little generator. It looks like a photocopy machine. You have it in your house, and the efficiency of capturing the heat off that little motor is so efficient that if it's working well,
Right.
you can heat your home water system and generate power for the home. So you're creating your own. So when I talked about that on a webcast, all the camera crew were rushing up to the internet as we were talking, because they all wanted to buy one, but they're 15 grand. Some have been sold, but they're still expensive. But in Japan, they're subsidized. But there's a good example, Doctor, of a very efficient little combined heat and power unit on a small scale.
Yes, so this is assuming that you got it, and then if you use it carefully, you can reduce the overall cost, consumer point of view. Yes?
I just wanted to mention the National Grid has got 5 free watts in central New York that we're playing with.
Oh, do you?
Yes.
Oh, that's cool.
They've been operational for about a year to 18 months.
That's very cool.
Great.
Very neat.
What is it?
Oh, it's a generator, a power generator for your home that and it captures almost 100% of the heat off that little motor. It's a little Honda motor, like a motorcycle engine, that runs almost silent in your home, making the electricity for your house. And the heat capture is so great that you basically can run your hot water system without. So it's called a free watt because you're paying for heat or paying for your light, either one. But you're only going to pay for one. You get both.
And you're making electricity with it.
Yeah, you're making electricity and salvaging the heat. So you're basically only having to pay for heat or if you're getting both. It's a neat system, and of
Yes.
course, there's larger versions of that for commercial application. But that's interesting that National Grid is experimenting with this.
And we have done work with other renewable energy, including its cost, maintenance cost, all of this. So just want to give you a snapshot of that. So if you do that optimization process, and you can see the reduction of cost. So this is if I don't do anything. Here, if I do the optimization, but know this, if I know exactly how much energy I need. But many times we don't know tomorrow or 15 minutes later what we need. So this is the forecasted, and this is another process we did. And what we found out, this optimization, this methodology, if we use it, you can see this is better when we do not know what is the data, when we do not have the actual data. But still, it is available, and we can do that with the 13 hours of CHP operation. Not 24 hours, 13 hours CHP operation. So this is one of the areas. The other area, so basically if I summarize, we said it can give you the energy cost saving, but another thing I did not show you the diagram, but basically we said it's not necessarily that you said, okay, I will buy a bigger one because I can afford it, but that's not going to really do what you are buying it for. So you really have to buy a right size, and along with the storage device. And we have said, you know, if you buy 50 kilowatt storage device, you said, no, why am I spending it? It is on sale, so let me buy 150 watt. It's really not going to help you saving the money. So we have done that, and as I said, this MPC, which is the model predictive control methodology, if we use it, when we don't know the actual value, we can still predict to some extent, and as I showed, the 66% of energy saving. Let's move on to another one. This is CO2, but it is also useful for, we just did it on that, I want to show you. Guess who does the most emission? Electric power, at least. This is not my data, this is published data. So just to show you on that. But the good news is, New York State is not one of the most emission. New York State is not. So that's good. Should be happy on that. So electric power thing. So what we did, we said, okay, this is a what we call 33 bus, system. So we said, okay, what happened if we include some solar cell or wind turbine in between? And so this and this one is the solar cell, this and this one is the wind turbine. Okay? But now, before I go, I want to another area which is, as Nick was saying, the problem of you don't know what it is. Well, one of the things nowadays coming up, at least in the research community, is isolation. So basically you can create, that's one part of the smart grid, say, okay, if I know somewhere here something happened. So instead of, so I can isolate this one and then try to fix it, that one, or I can isolate this one and say, look, I'm generating enough power to support this, so I don't have to do that. Those kind of different things are going on. So here we put 4 of them, and we said, okay, this is the price, dollar per kilowatt hour. That's how it is varied, and this is what we call load profile. That is how the load for that particular neighborhood. That's how it is changed. So the price, the load profile, and now we are putting the renewable energy. So we ran different scenario, and you can see how the power varies depending on what kind of optimization. And this is basically injected power from the, basically what we are saying is, if I do it correctly, that I can reduce the power from the grid, means usage. I don't need that much of power. So if there is some peak power, or the transmission line is full by its capacity, I can divert some of the power in a different direction so that it's not overly stressed. Yes?
Does that slide show, looks like it shows scenarios 1, 2, 3, and 4 being additive rather than comparative? I'm not really sure what it's...
That slide is basically, as I said, I have 4 renewable energy sources, and they are not operating 24 hours first. They are not capable of supplying energy in their peak maximum capacity 24 hours. So based on that information, I'm using whatever power they are generating in a particular method, so that my objective is to reduce the power intake from the grid.
Yes, but you didn't define the scenarios 1 through 4 that I understood.
No, I did. That's a different level. No, I did not. But as I did before, we tried many. This is just an example that how you can time it, and those kind of scenarios. I did not go through in detail. Those are within the mathematical equation. We just change the variables. That's basically. So this is, and then what happened is, if we do that different scenario, I mean, just for your example, different scenario could be, you can say, okay, no matter what, my wind turbine will always be on, whether it is generating 1 kilowatt or 50 kilowatts, or no matter what, I will keep my solar cell connected to the grid. That's kind of things. But many people say that, but the problem is, as I think someone asked the question, it's not easy to integrate those renewable energy with the grid, because you really have to synchronize those. And another project we are working to develop the circuit. You've got to get the information and then synchronize, for example, voltage level and the frequency, all of this. Then only you can say switch on, it is connected, or switch off, disconnect this. So that's a totally another area of research, and some of our students are working on that. But this one, we said, okay, if we do that, interesting thing is to note that some gives you some kind of savings, some really does not gives you anything. It's a negative, basically, not getting anything. And that's where the discussion comes in. I have renewable energy, it is in my circuit, but I'm not getting any saving. cost-wise. Now, with what can this happen? This particular one, I must mention, this particular one, we use what is in Europe. They have a CO2 emission penalty. We included that. And once we included that, we said, not renewable energy inclusion, not always save money. Okay? And if I do the calculation without considering the installation cost and what you call in general operation cost of renewable energy, I can always show you the calculation should you have savings. The moment you include those parameters, it's not always a saving. Yes.
Dr. Ghosh, I think the point that I'm seeing is what we just said. Nick just pointed out that some of the grid dates over 100 years old. The regulatory construct was all done in the last century, and the technology is moving so quickly that none of this is keeping up with the technology. So I think the opportunity here for all of us is that the regulatory construct has to catch up to the technology and convert the old grid.
Absolutely, absolutely. But yes, absolutely.
In order, I just go to your price of carbon.
Yeah.
We don't have a price of carbon here.
Right.
We have a price of carbon in Europe.
Right.
There's a price of carbon in Canada. There isn't a price of carbon in the US.
Right. Absolutely. So we have to be careful, and that's why I said the policy and the things we have to consider all aspects carefully to come up with some kind of solution. I'm not a policyman, I don't know anything. But another thing I want to point out, you see what happened is when, and Nick, and you can correct me, when you have a generating station and you send that, as Nick said, one-way supply of the power comes to your home, during that travel time, you lose some of the power, which is a power loss, and that varies. But I guess we pay for that power loss. I mean, customer pays for it. So one of the things, is there any way we can reduce that? And that reduction has a lot of benefit, not only price-wise, environmental-wise, and also the improvement-wise. So one of the things in the as Nick showed the distribution system, many people are saying instead of putting those renewable energy far here, put close to where the users are. So it will flow less direction and lost that. So here, quickly, you have a power loss. I'm sorry.
No, I apologize. I just want to say about 1 minute, please.
Okay. All right. So just to show you, this loss increases, and because of the loss increases, not only cost-wise, but CO2 emission increases too, because of the loss. So renewable energy has multiple effects, which can also reduce this loss. So, as I said, to minimize operation of the carbon emission, cost of carbon emission alone may not always encourage operation, because we don't have anything but some of the things we said. And we, as I said, we really need to carefully consider the operational cost of all of these before we said. Anyway, thank you.
Thank you very much.